the destroyer. Every day in Europe alone, it kills 12 people and severely injures 120, the vast majority of them in residential buildings. The killers are smoke and gas. The principal victims are the very young and the elderly. Naturally enough, we do everything we can to defend ourselves against fire. So many of the things we have around our homes, computers, fridges, furniture, beds, contain flame retardants. As the name suggests, they reduce flammability and delay the onset of fire. This saves many lives every day as well as protecting property. But surprisingly, some are known to be toxic and pose a very serious threat. We seem to have become addicted to cell phones. We buy more than 1 billion every year. And every couple of years we upgrade to a new model. These everyday items are amongst the fastest growing types of waste. They contain hazardous materials like metals and brominated flame retardants. Every year in the USA alone, people throw away 125 million phones. That adds up to 65,000 tonnes of waste from just one product. Now add to that all the computers, TVs, coffee machines, furniture, paint and upholstery that are replaced every year. And it'll give you an idea of the vast quantities of flame retardants which are being produced and then discarded. And they stay around for decades.
We use them a lot indoors. And they get into the environment maybe you could think of 3 different points. One is when they're produced. You have a factory that produces the flame retardant or it produces the plastics, and you have emissions coming from there, maybe into the water or into the air. And then in your house, you've brought in your brand new television set, and of course it's going to emit some of these constantly into the air, and it will get into your house dust. And this will maybe get washed up when you clean your floor, or you pour it down the sink and it goes into the waterways, it gets into the sewage system, into the sewage sludge and the water going out into the rivers. Or you've got a vacuum cleaner bag and you throw it into the trash and it ends up on the dump. And one day your computer is old and you want to get a new one, so you take that to hopefully your recycling center, but somewhere along the line it usually ends up also possibly in a dump. Then it's going to possibly release these compounds also either to the air and maybe even into water, because water usually, when it rains, percolates through landfills. And that goes out sometimes into the groundwater.
Treatment of electronic waste is not universally carried out to very high standards. In parts of Africa and Asia, improper treatment allows brominated flame retardants to produce even more toxic compounds like dioxins.
Of particular concern, perhaps, is the fact that you can detect a lot of these flame retardants in environments that are entirely remote from human activity.
Scientists are finding that many of these substances have made their way into the food chain. They can leach out of consumer goods, they don't go away, and they're toxic. Concentrated levels have been detected all over the world in wildlife, humans, homes, and even in breast milk.
In the 80s, Swedish researchers found the presence of brominated flame retardants in the human milk at substantial levels. And this was the first indication given by the chemists to the toxicologists that these might be compounds which were actually accumulating through the food chain into the human body.
It was actually at the same time where we discovered ourselves the PBDEs in sperm whales that were found stranded on the Dutch coast. And the 2 reports actually were both presented at the dioxin conference in the same session with a lot of people. There was a lot of attention, and we presented our sperm whale case, and the Swedes presented their human milk case. And the Swedes in particular had very interesting data because they showed a trend. So retrospectively they had analyzed human milk, I think went back into the 80s. And you really could very clearly see an increasing trend of these PBDEs in breast milk. And that was of course worrying, because at the same time we saw PCB and DDT levels going down, where we saw PBDE levels going up.
It was a clear signal that these compounds could accumulate in the environment, including the human food chain. And when that was seen, the toxicologists became interested in the toxicological effects, because at that time very little information was known about the toxic effect of these compounds.
People started to do research in their own countries, studying breast milk in Canada and in other countries, and actually all over the world we saw more or less the same picture. That was worrying. Then toxicologists took up the case and started to look into the potential effects of these PBDEs.
I would be mostly concerned about developmental problems. Developmental problems with respect to hormonal disturbances, cognitive disturbances, let's say learning capacities. From all evidence we have of these brominated flame retardants, the majority of these compounds points towards this type of effect, and the margin of safety with the human situation is not, which I would consider to be safe enough.
The discovery of some of these chemicals in human breast milk was, I think, quite a defining moment in gaining a broader understanding around the public and amongst decision makers. There have been some controls introduced, very welcome controls, especially within the European Union, restrictions on marketing and use of certain flame retardants, and also restrictions specific to use in electronics to try and get around this problem.
There is no universal flame retardant. There's no one flame retardant that works in all plastic systems. And in practice, I guess there are maybe 100 commercially available flame retardants. They fall into about 5 or 6 main types, but all of them have their different properties. Each one has its own advantage and disadvantage, but there are many different chemistries that are used.
It's a problem we really can't ignore. We have to act now. If we don't, we're leaving a toxic legacy for the next generation. Historically, some people say that the producers of flame retardants have failed to adequately consider the impact their products may have. That has to change.
As for many other situations where there has been a large commercial interest in continuing to produce a hazardous chemical, we saw the same sorts of reactions, unfortunately, coming from many sectors within the bromine industry, within the flame retardant industry more broadly, to defend their products at every stage.
So, whilst there's little doubt that we should use flame retardants, we really need to find alternatives that are less toxic. Some do exist which seem to be less toxic, but there's a catch. We don't really have enough reliable information about their possible effects, what harm might arise from exposure to them, or how effective they are at slowing the advance of fires. In fact, when it comes to detrimental effects, for all we know, they could be even worse than the ones we're using now. So what's being done about it?
We'll find at least part of the answer here. It's the Free University in Amsterdam, and its Institute for Environmental Studies is coordinating a complex and wide-ranging research project funded by the European Commission. It's called Enviro.
For the flame retardants with a very low water solubility, we are not doing these kinds of...
The collaboration draws on a wide variety of scientific disciplines and involves 12 European groups, from industries, small and medium-sized enterprises, research organisations and universities. Their aim? To replace hazardous brominated flame retardants with substances which aren't toxic.
One very important perspective that Enviro stands is a bit unique from other projects is the broad competence involved, from everything from toxicologists, from people working polymer chemists, people working with mechanical issues, the final application performance. You could just name it. It's a long list of sciences that meet in this project.
We have seen with these PBDEs and other brominated flame retardants, we actually have seen before. So I started to work in the 70s on PCBs, which were also used as flame retardants. And it took a long time to find these compounds, to discover them, to measure them. You have to develop methods. You start to report it, you start to discuss it. People like authorities start to establish tolerance levels for food. But at the end, people see that it's not really helpful, all these things, and you have to ban them. And it takes a long time and a debate with the industry and so on to ban the production and the use of, in that case, PCBs. Then after, you need alternatives. And again, there is time needed, sometimes a long time, to develop alternatives. On and on, doing more or less the same thing, going through the circle, repeating it, and every time it takes maybe 5 to 10 years.
The sort of investigative cycles Professor De Boer describes seem wasteful. The Enviro Project is taking a practical approach based on chemical substitution, which tests alternative flame retardants for their environmental, toxicological and flame retardant properties.
In Enviro, we developed an alternative substitution cycle approach. This approach consists of 4 major steps. The first step was a prioritization and selection phase. So we listed an array of all the possible alternative flame retardants. Then we've done a prioritization, we selected the most viable ones, and then we went to the second phase. And in the second phase, which was really a major task of Enviro, we looked for fire performance, the technological applications, the hazard, the exposure. And based on this information, we went to the third step, which was the risk assessment. And there we combined the hazard with the exposure information. Based on all the information, we went then to the big picture, the impact assessment. And we have done that with a lifecycle assessment approach.
In a lifecycle assessment, we try to map all the phases through which a product goes, from raw material mining to production to the use phase to the waste phase and recycling if possible, and try to quantify all the environmental impacts in all of these phases to arrive at a final complete score for the sustainability of a product.
This gives the whole idea of what we have done in Enviro, these major 4 steps. And that's really important, to work on these 4 steps.
It's also looking at, do these compounds change plastics? Do they work as fire retardants? Do they reduce the amount of soot or toxic fumes coming out when the plastics burn? Are they actually viable as flame retardants, not just as chemicals that don't cause problems? As far as I know, there aren't any other projects that have included both parts of this.
One interesting and rather unusual aspect of this project is the involvement of representatives of the industry. This is pragmatic cooperative research, which considers how practical the suggested alternatives are. The researchers chose and studied product combinations using metal-based, phosphorus-based and nano-clay-based flame retardants in 5 applications: printed circuit boards, electronic components, injection moulded products, textile coatings and intumescent paint.
What we will do today is showing the last results of Enviro.
Part of the project was an impact assessment of brominated flame retardant substitution. This involved interviewing a number of stakeholders in different phases of the flame retardant life cycle: producers, users, recyclers, NGOs, etc., and studying the literature to analyse the drivers and barriers of the substitution process from a social, economical and environmental perspective.
Green bacteria. And you look for luminescence, so if it gives more light there is more toxicity.
There was a stakeholder forum in which stakeholders from industry, government and NGOs were invited to share their experience and get informed on the project. It's all designed to establish levels of agreement rather than identify differences or reach a consensus.
We found it very important to involve stakeholders, which means producers of the brominated flame retardants and alternatives, and also producers of final products in which these compounds are being used.
The Stakeholder Forum, which surrounds Enviro, I think is also an incredibly important part of a project such as this. It gives the opportunity for greater understanding, for transparency, and hopefully for breaking down some of the polarization that may otherwise exist in the debate on flame retardants and future solutions.
The result of all this cooperative endeavour was not some abstract theory, but the actual production of application prototypes. They were rigorously tested using technical and other criteria, and the performance results were compared with those of traditional bromine-based systems. The big question is, were they any good?
The fire performance results showed that all of the 14 selected alternative flame retardants fulfilled the fire requirements. So we studied different fire performance characteristics like heat release and ignition time and efficiency, and all of these were similar to the brominated flame retardants. But I think much more important is even that we showed that the alternatives had reduced smoke yields compared to the brominated flame retardants. And this is really important because you have to realize that 80% of the fire deaths are caused by smoke. And therefore this is really important to reduce the smoke amount. Some examples, for instance, we studied ALPI in combination with MPP and zinc stenate as a synergist. And there we saw really a significant reduction in smoke yields compared to the brominated flame retardants. But the fire performance characteristics were as good as the brominated ones. In Enviro, we studied also flame retardants in polymer blends, and all of these fulfilled the fire requirements. The performance of the material was less than for the brominated flame retardants, so there's some room to improve these types of flame retardants. We studied also textile coatings, and we found very good viable alternatives which had good fire performance, but also from the application side they showed good results. An example is, for instance, APP combined with MPP and PER. This is really a good textile coating alternative. We studied toxic effects of these 14 alternative flame retardants, and we found that about 6 alternatives showed less toxic than the brominated flame retardants. What we also found is that they didn't accumulate as much as the brominated flame retardants. And for instance, for printed circuit boards, we found that DOPO is really a good alternative for some of the brominated compounds. For epoxy resins, for instance, you can use MPP combined with ALPI. This is also a really good alternative for the brominated compounds.
Mechanical and processability tests showed that the alternatives are just as good as the brominated flame retardants and in some cases have improved viscosity. An efficient intumescent paint to protect hips was also developed. This showed a shielding effect from the char protecting the polymer and an absence of added heat flux from the flame. There was both reduced smoke and a negligible heat release.
Breakthroughs in research often occur as a result of refining techniques or changing the approach entirely. This European Commission project decided to adopt a method which would speed up the whole data acquisition process and invite input from stakeholders in both the theoretical and practical aspects of the problem they were studying. If the approach adopted by the Enviro team is adapted elsewhere, it'll help us to short-circuit the business of countless years of monitoring, analysis, toxicity studies, debating and legislation.
Well, the success of the Enviro project, I think, is really demonstrated by the fact that we really found alternatives.
It's extremely important. We get a broad view on the physical, mechanical properties, on toxicology, on ecotoxicology, on the prototype performance of commercial products on the market that used to be the major consumers of brominated flame retardants.
The Enviro Project is something that we have very much welcomed, along with other types of projects that aim to engage a very wide range of stakeholders, including industry, including NGOs. I think with this type of project, you have the opportunity then of bringing in a vast array of knowledge and experience that may not otherwise be available.
I think the major breakthrough is also that the approach can be used for other chemicals. So it's not only limited to flame retardants, but there are many chemicals which have to be replaced because of hazardous effects. And this is an approach how you can do that.
The critical objective was to demonstrate that there are commercially available flame retardants, halogen-free flame retardants, which can replace the brominated flame retardants. And that's been achieved, so I'd say on that basis, it's been a successful project.
We really have demonstrated that within a period of 3 years, together with industry and with other scientists from other disciplines, we can offer something, and that is a good achievement, I think.
Its success not only helps us to identify viable substitutes for the toxic BFRs, but also establish a methodology that could be used for studies of other undesired substances or high-volume production chemicals. They may well have done future generations a big favour.